Hello everyone, I am Shixun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, we want to talk about half transform, which is a well-known algorithm for detecting the shape of objects from their boundary points. In this video, we take the light detection as a case study for detailing half transform. The outline of this lecture includes introduction about the history, purpose, and the idea of half transform, detection algorithm about two steps of half transform that are shape parameterization and parameter voting. Half transform is an algorithm originally patented by P. Half in 1962. It was firstly used for detecting lines and simple polygons by Duda and Hart in 1972. Then, it was generalized to detect arbitrary shapes in 1981. The main purpose of half transform is to detect the shape of objects from the boundary points, but in presence of imperfections. The imperfections are generally from three aspects: missing points. Some boundary points are not detected from edge detector. Extraneous points. Some detected boundary points may come from other objects. Noise. Some non-boundary points may also be detected as boundary points. By taking light detection as an example, we explain what are missing points, extraneous points, and noise. For an image with two lines, we can extract their boundary points by using any existing edge detector, such as Sobel or Canny edge detector. In this example, the edge detector may miss detecting this boundary point, namely missing point. For detecting this line, these three green points located in the other line are called extraneous points. This non-boundary point, but detected, is called noise. How to address these three imperfections? Half transform has the answer. Firstly, half transform is a global approach that uses all boundary points for shape detection. This permits misdetecting some boundary points. Then, half transform uses a voting scheme for estimating the shape parameters. It counts the occurrence numbers of the parameter values and takes the parameter values with higher votes as the estimation results. Through voting scheme, half transform alleviates the effect from extraneous and noisy points. For light detection, half transform estimates the parameters of a light equation by using all boundary points via voting scheme. In general, the light equation can be expressed as y equal to as plus b, where a is slope and b is intercept. For voting parameter values, half transform creates an accumulator of a and b. A and b are ranging from a minima to a maxima and b minima to b maxima respectively. For the first point, we vote the parameter values of all possible lines passing this point. We do the same thing for the second point until the last point. the parameter values with high votes determines the detected line equations. In this example, these two parameter pairs with 4 and 3 votes respectively determines the green and the blue lines in the image. The first step of half transform is shape parameterization. It is to formulate the shape detection as parameter estimation problem. As mentioned, line detection problem can be formulated as AB estimation problem. Since half transform uses a voting scheme to solve parameter estimation problem, all parameters used for voting must have finite range. Unfortunately, A is a slope and has infinite range as the line approaches to vertical. To address this issue, half transform places line equation in rho and theta instead of A and B parameter space. As shown in this figure, rho is the distance between the line and the origin, and theta is the angle of the vector from the origin to the norm. Therefore, half transform places the line equation as s cosine theta plus y sine theta equal to rho. Here shows the derivation of the line equation in rho and theta parameter space. In this right triangle, the length of hypotenuse is obviously rho over cosine theta, and the last point P has the coordinate rho over cosine theta 0. In this right triangle, since this angle is also theta, its hypotenuse length is rho over sine theta, and the point Q has the coordinate 0, rho over sine theta. By using these 2 points P and Q, the line slope A can be computed as this equation, and equals to minus cosine theta over sine theta. The intercept B is directly rho over sine theta. Then, by substituting these 2 terms for A and B, the line equation y equal to AS plus B becomes this one. After multiplying sine theta at both sides and moving this term to the other side, we have line equation s cosine theta plus y sine theta equal to rho. Then, we discuss the range of rho and theta. The range of theta in clockwise direction is from 0 to 90 degrees. Take this red point as an example. Theta is 0 in the case of the vertical line passing this point. Theta is 45 degrees in this case. Theta is 90 degrees when the line becomes horizontal. In counterclockwise direction, the range of theta is from 0 to minus 90 degrees. This line shows the case of theta equal to minus 45 degrees. Putting them together, theta is in the range from minus 90 degrees to plus 90 degrees. For the range of rho, it has a minimum value 0 in case of the line passing the origin. For an image with the size W by H, the maximum row is square root of W squared plus H squared when the line passes the furthest point. Since the cosine theta or sine theta may be negative, the row is lost in this range. After expressing the shape with the finite range parameters, the second step of Hopf transform is parameter voting. We firstly quantize the parameter space into several bins, and then create a parameter accumulator array. In this example, with an A by A image, parameter row is in this range as discussed. That is from -12 to +12. By quantizing rho and theta into the bins whose interval equals to 1 pixel in rho and 1 degree in theta, we can create a parameter accumulator as this 2D table. The accumulator A of rho and theta is shown in the form of an image with the size 25 times 181. After that, we sequentially take all boundary point P of Sy for voting all possible parameters. In line detection example, we range theta I from -90 to +90 to compute all possible lines passing through this point. For each theta I, we compute the rho I according to this equation, and increase the accumulator bin A of rho I theta I as this equation. In this example, we take the first point at the coordinate 1, 1 for voting. The lines passing this point will satisfy this equation. This table shows the rho and the theta values of the lines passing this point. The red line shows the voting path from this computed rho and theta values, which is a sinusoidal curve. For the second point at 3, 2, this table shows the rho and theta values that satisfy this equation. In this figure, the green line shows the voting path of this point. After visiting all boundary points, we have all voting curves of them as shown in this figure. The parameter values of these two bins that most curves intersect determines two detected lines in the image respectively. In this video, we introduce a Hopf transform consisting of shape parameterization and parameter voting for detecting the shape of objects. For detailing Hopf transform, we introduce the line detection as a case study. Hopf transform expresses a line in rho and theta space and votes for possible rho and theta values by using all boundary points. Thanks for your listening and have a nice day.